Now we're faced with the most important theorem in all of calculus, the fundamental theorem of calculus. So what I'm going to do first of all is sort of warm you up to something, and then we'll see how you feel about it. When we're doing the definite integral, we always had a number in the bottom and a number at the top, the limits of integration as they're called. But this time, I am just going to suppose that x is greater than or equal to 2, it really doesn't matter. So what I'm going to do is do a few examples to show that there's a few definite integrals we're capable of getting formulas for, but not a great deal, many of them. I'll show you the ones we can work with now. Now I want to put up here in this upper limit a variable exponent, or a variable upper limit of integration. So if we were to graph this thing, here's what you have. If we were to graph the function that is just 3 on the interval, from 2 to x, then I could mark a 2 here, say, and then an x here, say, and then the value of the integral would map out the region in this rectangle. Well, what's the base of this rectangle and what's the height of the rectangle? We know the height is 3. The base is x minus 2. So the integral from 2 to x of the number 3 dt. We use a t so that we don't, I probably should use a t on for the x-axis, but x is just a number on there as far as t is concerned. So you can see that it is the base times the height, 3 times x minus 2. Or if you want, this equals 3x minus 6. I think it's interesting that you should note, though, so we have the integral from 2 to x, 3 dt. I kind of lost what I was going to say. Over here, you have 3x minus 6. What I'm going to do is take the derivative of both sides. So that amounts to taking and putting a d over dx on the left, and a d over dx on the right. Well, notice that when I take the derivative of the right-hand side, the derivative of 3x minus 6 is simply 3. And you notice that matches what's inside of the thing before I took its integral. Let me try another one. Try the integral from the 3 to 4 of x, nope. 3 to x of t minus 2 dt. Alright, so if I'm graphing t minus 2, this would be t, and then a negative 2, say, is around here. This has an x-intercept of 2 and keeps on going. We are interested in 3 to x, so let me put a 3 here and then an x here, and I'll make the requirement here that I'm going from the interval from 3 to x. X, of course, is going to be positive, bigger than 3 as we need. So the length of this base is x minus 3. The height of this thing is x minus 2. You just take x and you plug it in. So what's the area of this trapezoid? Well, one of the formulas for the area of that trapezoid is one that's kind of like a triangle area. And it's kind of like a triangle, except you got a lower base and an upper base. The lower base has height 3 in for t of 1. So anyways, the formula for a trapezoid goes like this. It's 1/2, and then it does base 1 would be the lower base, so x minus 2 plus base 2, which would be 1, and then times the height, which was x minus 3. And let me go ahead and multiply this out. 1/2. This will be x minus 1 times x minus 3. And if I multiply that out, I'll get x squared minus 4x plus 3. That's the value of my integral. And so, to see if I did it right, I'm going to check by taking the derivative of my integral, or at least the function that I found here, and seeing if it matches the t minus 2. So now I'll take the derivative with respect to x. I probably should have snuck it in over here. That's going to equal, now for the 1/2 doesn't matter, so I'll still have that hanging around. But the derivative of x squared is 2x. The derivative of negative 4x is minus 4. And then if I divide through by 2, I have x minus 2. Notice that had this been an x, we're using a t so that it doesn't confuse with respect to the variable of the x of the upper limit. So you can see when x is t, t minus 2 matches the derivative. Here's another example. Let's just do mt plus b. And we will go from, I don't know, a to x. None of these letters obviously don't mean anything, except for the x is the variable, dt. What I would like to know is a formula for this particular integral here. Of course, I don't want m to equal 0, because I actually want it to be not a horizontal function. So if you look at it, if this is the graph, t is the x-axis, then b may or may not be below it. But then whatever happens, it's going to cross at some point because m is not 0. What is that point? Well, that's negative b over m. So anyways, depending on where a is located and all that, I could end this at x, and let's just say I don't care, a is out here somewhere. So I'll continue this line so that a can have its time as well. So then what I'll have is I will have a triangle where the base is x plus b over m. The height is mx plus b. But then you've got this piece here, which is all negative stuff. Let's see. The area of this base, or the length of this base, is a plus b over m. Actually, I got it backwards. I did not realize I would get rid of all that, so let me put that back if I can. Okay, so the base, the length from here to here would be negative b minus m minus a. Negative b over m minus a. And the height of this thing would be ma plus b. Alright, so let's take a look then. If I do the integral from a to x of mt plus b dt, I'm going to get this here, which will be x plus b over m times mx plus b minus this triangle down here. So we have, that's negative b over m minus a times ma plus b, and that's actually times 1/2 because you're dealing with a triangle as well here, so you got to go 1/2 base times the height. So let me multiply it all out just so I get a formula for this thing. I'll do x times mx, that'll be mx squared. I got x times b, so I got plus bx. And then I have b over m times mx will be plus bx again. And then I have plus b squared over m minus, well actually, you know what, I'm going to change it to a plus. That way I can have 1/2 b over m plus a times ma plus b. I don't care about this. This is the formula for the integral. Now notice what happens when I take the derivative of it with respect to x. That t should match the variable inside of the integral. So it's d over dx. We are going to have mx squared. And I think I missed a 1/2 that was attached to here. So all of this is divided by 2. Plus, then I'll have 2bx. And then all this stuff here is just a constant, so I'm just going to put plus c for that stuff. And when I take the derivative, I would have had these over 2. So let's see what happens. That's going to equal, here I'll get 2mx, and then I'll get 2b. The constant, of course, will disappear. And if you look, I have mx plus b, which is the same thing as what was inside, the same thing as the integrand if the t were an x. Next, I have an example out of the current textbook we're using, and it looks like this. I am more interested in this function here, capital F of x equaling the integral from 3 to x of f of t. So I'm interested in finding these values here. So let's take a look at f of 3. Well, that's going to be the integral from 3 to 3 of f of t dt, which automatically equals 0. F of 5 is the integral from 3 to 5 of f of t dt. Now the 3 to 5 is in this area here, and we're told the area equals 3. And then f of 9, that's the integral from 3 to 9 of f of t dt. And that equals, so if I go from 3 to 9, I'm starting here and ending here. So I got positive and negative area. So I'll take 3 minus 35. in each of the cases that I showed, the derivative from a number to x, f of t dt equals f of x. This would have the effect of undoing the integral, if you will, because the derivative of the integral is erasing the integral basically and plugging x in. And that in fact is the fundamental theorem of calculus, part 1. And the statement goes like this. Suppose f is continuous on the closed interval a to b, and let capital F of x equal the integral from a to x of little f of t dt. Okay, so once again, I'm going according to the rules, not according to the rules, but rules of etiquette, I suppose. You don't want to use the same variable inside. Remember, this variable inside is just a dummy variable. You could use anything you wanted to, including x if you wanted to, but I think that would be a mistake since you're dealing with an x out here. So basically, f of x is dependent on this upper limit. You saw that in some of the examples that we did. Well, here's the gist. Here's what we have then. Then capital F prime of x equals little f of x, and capital F is differentiable on the open interval AB and continuous on the closed interval AB. What we're going to do for the proof of this is I am going to recall the definition of the limit, or the definition of the derivative, the limit definition. If you remember, f prime, capital F prime of x equals the limit as h goes to 0, capital F of x plus h minus f of x all over h. So I'm going to work that formula if I can. First thing I want to do is look at f of x plus h minus f of x. Let's take a look at that thing. Well, that equals a to x plus h little f of t dt minus the integral from a to x little f of t dt. Now, one of the things I'm going to do is suppose h is greater than 0, just for now. So I'm kind of doing a left and right hand kind of a limit, I guess you would see. I'll put that in a little bulleted point and I'll continue equaling here. You'll remember then that the first integral can go from a to x f of t dt plus the integral from x to x plus h f of t dt. Then we have minus the integral from a to x f of t dt. So I can cancel the integrals from a to x, and all that I'm left with so far then is the integral from x to x plus h f of t dt. Now, one thing you ought to know is if I have my function coming along, wave, and I want to just now talk about from x to x plus h. This is really zoomed in so that you can see some of the details. Well, on this interval, the closed interval from x to x, h, since the function is continuous, we have an absolute maximum and an absolute minimum. So on the interval x to x plus h, f of x has an absolute max and an absolute min. So let's take a look on this picture. What would be the absolute max? It looks to me like it's actually occurring at x. So what I'll do is I will create a rectangle of that height, and we can see that the integral is less than or equal to that height. So what we'll do, just according to this picture, what we're going to do is let capital M be the abs max, and let lowercase m be the abs min. And they occur at some value within the interval itself. If I look, then if this is the highest point, then this is a capital M. So no matter what you have, is the length of this base is h. You take this minus this. So the integral from a to, not from a, from x to x plus h, is most definitely less than or equal to capital M times h. And the same thing is true if you find the absolute lowest right here. Could be the absolute lowest. It's pretty clear from the picture that no matter what you get for the value of the integral, it's going to be at least as big as little m times h. Base times height is little m times h. And so now let's take a look at this interval in some more detail. Remember, I'm trying to actually get the value of the integral here between x and x plus h. And whatever it is, it's between these two values. Well, what happens as h goes to 0? What do you think is happening to what, let's say this here would be little m, and my picture has changed from the previous one. Say this here is capital M. Well, what happens as h goes to 0? I mean, these things are trapped between x and x plus h. If h is going to 0, this is shortening the interval. So allow h to go to 0, and you can see that this x plus h is going to go to x. That means that as you move along, the maximum of the interval will also move along with it. And what will it be doing? It'll be getting closer and closer and closer to what, in this case, or in this example, would be the m value, the littlest m value. And then as h keeps on going smaller and smaller, what's happening? Even this m value is getting shoved to x. So I'll say this, as h approaches 0, m is approaching m. Capital M is becoming the same size as m. Inequality, series of inequalities, little mh, almost a b, less than or equal to the integral from x to x plus h f of t dt, less than or equal to capital M h. Since h is positive, I'll divide everything by it. Now then, let h go to 0. What does that tell you? If h is going to 0, m is approaching m. And so, this thing in here must equal what they all become. So this is basically just the squeeze theorem here. As h goes to 0, since m is approaching m, that forces the limit in between to equal the same as all these things. Now these m's were variable, so you ought to be careful about that. As m is going to m, what's going to the value of x? Well, if it's trapped in between, or the value of f of x, it's trapped in between lowercase and uppercase m. That means that as h gets closer, it's also going to force capital M and little m to go and equal x. Well, f of x. Let's do some examples. D over dx, the integral from 3 to x of tangent of the square root of t dt will simply equal tangent of the square root of x. So I simply replace t with x. How about d over dx of the integral from x to -1 of ln absolute value of t dt? Well, remember the theorem has the x in the upper limit, so this equals d over dx, and I can put a negative in front of it because I'm going to switch it to -1 to x, put it upside down, ln absolute value of t dt, and that will equal negative ln absolute value of x. D over dx of the integral of 0 to x cubed of 1 over t squared plus 1 dt will equal, once again I'll take the upper limit and plug it in there, so I'll get 1 over x cubed squared plus 1. But now this is interesting, since this is a function, you have x cubed is a function inside of the function, so I have to use the chain rule and take the derivative of what's left inside. And that'll, of course, be 3x squared. And if I want, I can multiply this out, get x to the 6th plus 1. The next theorem is the fundamental theorem of calculus, part 2. There are no more parts. This is the last one. Suppose that f is continuous, little f is continuous on a closed interval a to b. If capital F is an antiderivative of f, little f, on the open interval a to b, then the integral from a to b of little f of t dt equals capital F of b minus capital F of a. Proof. Let capital A of x equal the integral from a to x of little f of t dt. And x I'm going to force to be between a and b. So on the open interval a to b. Now since a prime of x equals f of x, which does happen to equal capital F prime of x because f prime is an antiderivative, a of x minus f of x is a constant. Now let's take a look at some things. Capital A of x equals the integral from a to x f of t dt. If I plug in a of little a equals the integral from a to a f of t dt, and we already know that equals 0. I remember mentioning it. They call this the zero width rule because you have no thickness on there. And then what is capital A of b? Well, capital A of b equals the integral from a to b f of t dt. Well, that's nice because that's actually then that's equal to capital F of b plus that constant I mentioned. So I think I mentioned a of x should equal capital F of x plus this constant. That's why I put it there, because when you have a of b, that equals f of b plus this constant. Capital A of little a equals 0, but that's still f of little a plus c. And then so we have capital A of b minus lowercase a of a, capital A of lowercase a. On the one hand, that's the integral from a to b of little f of t dt minus the integral from a to a f of t dt, and I know that this equals f of b plus c minus capital F of a plus c. but everything zeroes out. For instance, this integral is 0, so we're left with this integral right here, the integral from a to b of little f of t dt equals capital F of b minus f of a. And this will provide us with ways of evaluating integrals from here on out. Basically, this f is an antiderivative. So typically, capital F of x is an antiderivative of little f. So capital F prime of x equals little f of x. Let's do some examples. Let's try the integral from 1 to 3 of x cubed minus 3x plus 1 dx. What it's telling us is basically if I can find an antiderivative of this, and we've done antiderivatives of these things before, that's not a big deal. What is the antiderivative of x cubed? Well, that's x to the 4th over 4. Then what's the antiderivative of negative 3x? Well, that's negative 3x squared over 2. You're running the power rule in reverse, and the derivative of 1 is x. Now, I don't have to put a plus c because if you'll notice in the proof here, the c's cancel out when you're doing the f of b minus f of a. So what we do to do capital F of b minus f of a is we typically write this vertical bar. I'll put a 1 on the lower part of it and a 3 on the upper part of it. And what we do is we plug 3 into this stuff right here. This is like our capital F of x. Let's plug 3 into it. So I'm going to have 3 to the 4th over 4 minus 3 times 3 squared over 2 plus 3 minus, and now I plug in the lower limit. This is the capital F of a. I'll have 1 to the 4th over 4 minus 3 times 1 squared over 2 plus 1. And so this is the value of the integral. Let's go ahead and simplify as much as I can. I'm going to get 81 over 4 for that part, 81 over 4. Here I'm going to get 27 over 2 plus 3, and then the minus will come through, make this minus 1/4 plus 3 halves minus 1. So let's put everything together. Well, I'm going to start with 81 over 4 and 1/4, the minus 1/4, and I'll get 80 over 4. Let me get rid of those things. Negative 27 over 2 and 3 halves is negative 24 over 2, so I'll get rid of those things. And then 3 minus 1 will end up being 2. And then none of these will be fractions. I'll get 20 minus 12 plus 2. That will equal 8 plus 2 will be 10. Let's try the integral from 0 to pi over 2. 0 to pi over 2 of 3 cosine of x dx. Well, as before, you should note that the 3 is not going to be anything. What's the antiderivative of cosine of x? That's sine of x. So I have 3 sine of x. And I'm going to evaluate that from 0 to pi over 2. So that equals 3 times sine of pi over 2 minus 3 times sine of 0. That equals 3 times 1 minus 3 times 0. That equals 3. Try this integral, 1/16 to 1/4 the square root of x minus 1 over x dx. I think the best thing to do is to break this up like radical x over x minus 1 over x dx. And then that will give me the integral from 1 over 16 to 1/4. This right here will give me 1 over the square root of x, or x to the negative 1/2. And this one I'll leave alone because I know that an antiderivative for that is ln of x. So this equals, remember what you do, add 1 to the exponent and divide by that exponent. So I'll have x to the 1/2 all over 1/2 minus the natural log of the absolute value of x. And that's from 1/16 to 1/4. That's going to be 2x. Since these numbers are both positive, the absolute value will not be necessary. ln of x from 1/16 to 1/4. I don't know why I did that. That's 2x to the 1/2. Now let's go ahead and plug in our numbers. So I'll plug in 1/4 first of all. So I have 2 times 1/4 to the 1/2 minus ln of 1/4. And then we'll have minus the second piece will be 2 times 1/16 to the 1/2 minus ln of 1/16. So this equals 2 times 1/2. 1/4 to the 1/2 is 1/2 minus ln 1/4 minus, then we have 1/16 to the 1/2 is 1/4. 2 times 1/4 plus ln of 1/16. And that gives me 2 times 1/2 will be 1. And then I'll have minus, I'll do the number parts here first. 2 times 1/4 will be 1/2. And then this stuff here, I can do ln of 1 over 16 divided by 1 over 4. So this is going to equal 1/2 plus ln. When you simplify this fraction here, you get 1/16 times 4 over 1 will be 4 over 16, or 1/4. And there's your final answer. All right, here's an example from the textbook that I've decided might be useful. I've stretched it out so I can see it. So that's why the letters look so strange. But we have the function of a graph of f of t dt, and it says that capital A of x equals the integral from 0 to x of f of t dt, where x is between 0 and 17, so it must end somewhere out here. Assume that the four regions R1, R2, R3, and R4 all have the same area. Based on the graph of f, do the following. So let's see here. Find the zeros of A on 0 to 17. Let's see, part A. What do we have? From 0 to 17, you have a positive region here, then this would be treated as negative area, and this is supposed to be the same as positive area. So what you'd have then is, by the time you got to 8, you would have a 0. So f of 8 would be 0. Or I'm sorry, A of 8 would be 0. And then let's see what else happens. Then it zeroes out again by the time you get to 16, because you gain some area here, but then you would erase it by the time you get to 16. So I see that capital A of 16 would also equal 0. Now what do we have next? Find the points on the closed interval 0 to 17, in which A has a local minimum, or local maximum, and a local minimum. So let's take a look. A local maximum would occur when you're at your highest possible y value. And so let's do the local maximum. And take a look what happens here after you leave region 1. So a little before 4 and a little after 4, let's say. You can see that by the time you get to 4, you would have the most area you could possibly have under this curve, because as soon as you get past 4, you'll start taking away area. So you'd have a local maximum at 4. So a local maximum happens at 4, comma, f of 4. I keep doing f of 4 when it's actually capital A. So let me fix that. And then the same thing would happen. Since it zeroes out again, it basically resets by the time you get into R3. So as you're gaining area, you gain the most amount of area you have until you get to 12. So you would have 4 12, capital A of 12. Now, when are you going to have your most minimum? Your most minimum, here, if you think about it, if you're going from 0, you're starting at 0, that's what it says on the integral. If you're starting from 0, then you're going to have positive area. You're going to have, it's going to be positive. It's still going to be positive. The only time it'll even get to 0 is when you get to 8. So the lowest it can possibly be is at 8. Actually, what do I want to say here? A local minimum. The smallest the function's value is 0, and that occurs when x equals 8. So local minima. We have 8, comma, f of 8. And the same thing happens over here. You're going to have your least amount at 16, comma, f of 16. And it just so happens that f of 16 and f of 8 equals 0. So, and then it says sketch a graph. I guess it's a pretty crude graph, to be sure. Let's go ahead and do that. What I'm going to do, the old days of sketching a graph meant that you would make up a chart and you would give me x values. So I have 4, 12, 8, and 16. Let's go ahead and put those in. So x, 4, 8, 12, and 16. And then I have the y values. Let's see, what is f of 4? Well, that's R1. I don't know if they told, did they give us the values of these things? No, all I know is that it's R1. And then I have f of 8. I did it again, didn't I? A and A. Anyways, so I should probably put, instead of the y, let's put A of x. Alright, so then 8, I know that that value is 0. And then at 12, I know that the value is R1 again, because R1 and R3 is the same. But then by the time you get to 16, it zeroes out again. So if I made a picture of this, let's say this is R1, I would have, and of course 0, 0 is right here. Then we'd have 4 R1, so let's say there's 4 R1, and then I would have 8, 0, put a dot there, and I have 12 R1, put it the same height that we had R1 before, and then 16, 0. So it's going to go something like this. It'll curve probably not much differently than the functions you were given. So it's going to be some sort of a periodic curve, just like the original one was. So let me fix that a little bit. Let me try to make it look a little bit better. Something like that. I suspect that these humps have the same amount in them, and that the same amount of curving happens. It's got symmetry and all that kind of stuff.